And so how do you want to handle questions? Just people interject, or
I actually have a
uh,
slide about that, but basically I'll be stopping every once in
okay,
a while to take questions. And I have some extra information for those that might want to ask questions. Uh,
okay,
we'll get to that. So anyways, welcome to the
right,
Greater Lansing area for SQL Server User Group, otherwise known as GLASS. And you can see today's date here. We are going to talk about linear regression in SQL Server and how to calculate it in SQL Server. And this was written for beginning data analysts and some experienced data analysts that might not know that you can actually do this in SQL Server. You know, a lot of people do it in Power BI, or they'll do it in an Excel spreadsheet or whatever. They don't know that you can actually do this in SQL Server. And one of the examples that we're going to use is something that's near and dear to my heart as a DBA, disk growth forecast. In other words, well, we'll see more about that. We'll get into that real deep, but it's very similar to what data analysts have to do for forecasting. My name is Jeff Moden, and up here in the upper right-hand corner, you can see my public email address. If you have some questions, or you might want to have some help on setting up a quick little lightning round for this group, or something like that, go ahead and send me an email with the understanding that I am a full-time employee, and that email address is for the public. And so it may take me a day or two to give you an answer. Please be patient. I'm not ignoring you. I have to keep my priorities together. Alrighty, so here's a little bit more about me. I am the fellow that coined the term rebar. And yes, it is pronounced rebar with an E in it, very much like the little metal rods hopelessly stuck in cement forever and not going anywhere fast, which is a general description for rebar code, not going anywhere fast because it's row by agonizing row, which is what the acronym stands for. I also help make the tally table a household name. You might know it as a numbers table. And as we were talking about before, Itzhak Ben-Gan came out with his get nums function, and I have an effing tally function that is a little bit different than Itzhak's. Itzhak's is more flexible. Mine will only count from 0 or 1 up to some number, and only in whole numbers. And the reason why I do that is because that solves 99.9% of what I would use it for. So, and if I need something else, I'll use Itzhak's or some other little chunk of code. Now, I love SQL Server. When I found out I didn't have to write loops anymore, I just absolutely fell in love with SQL. So it's not only my profession, but it's also my hobby. And I do it pretty much to the exclusion of everything else except for drinking coffee and breathing. And that is actually the order of importance. So yeah, I know I need to get a life, but I have a face of radio. Hopefully you think I have a voice for radio as well. As we said, for questions, I'll occasionally stop to see if there are any questions. But for previous slides, and typically we're going to be going fast enough where they will be previous slides, please include the slide number, which is down here in the lower left-hand corner. And that will allow us to very quickly jump to a slide, and we can answer your questions there. Now, I'll also tell you that this presentation was set up to be an hour long, but this is a user group and we have 90 minutes allocated. So I've added a little bit of a couple of little things here that we can have added in to make us understand a little bit better about what is linear regression. And I'm sorry about my throat here. So why do we want to use it in SQL? Well, first of all, what it is, to summarize, and this quote came from Britannica. Basically, you're doing curve fitting with straight line. You're taking data and you're saying, okay, what's the general trend here? And in fact, in SQL or in Excel, these are called trend lines, and we'll see those in operation during this. But my definition of it is a little bit more sincere. It allows you to do forecasts and predictions based on previous history. And this includes financial and a whole bunch of other forms of insight. For example, compared to the temperature of the day, how many ice cream cones are you likely to sell? And that's a form of linear regression as well. And that's a very typical example when they're teaching linear regression. It's also one of the fundamentals of machine learning. If you look up machine learning, the first thing they do is they teach you a little bit about linear regression. Okay, now at this point, Mike, I just want to double check. Are you hearing me okay? And I'm not, I'm still connected, right?
Loud and clear.
All right.
No jitters, no nothing. So you're sounding good.
Okay, because I gave a presentation once where I talked for 20 minutes and found out I was disconnected. That was fun.
I had to stop you earlier, but no, you're good. And the video's coming through good.
Okay, good. So we're going to cover two basic types of linear regression. One is just a 2-point linear regression, and that's where you use just the starting and the ending points, and you ignore all the variances between those 2 points. There's no skew by intermediate outliers, and it's not always the wrong thing to do, but it's also not always the right thing to do. And this is what they have data analysts for, is to make these kinds of decisions. And then there's multi-point, and this is where you consider every single point in your regression, and we'll see an example of that as well. These are pretty simple examples. But again, it's not always right and it's not always wrong. And linear regression is not always the answer. We'll see that here in just a minute. When do you use it? That's mostly beyond the scope of the presentation, but the correct answer is it depends, and it can rely heavily on the shape of the data. For example, an exponential or a polynomial analysis may be better to fit the data with rather than linear regression. And there's a fellow by the name of Anscombe who wrote an example. It's a classic example for linear regression and this very thing that I'm talking about. And the wiki, the link for it is down here at the bottom for the wiki. And what he did was he made a chart, or made some data and then made a chart of it. And it's a very simple linear regression example. And, you know, we've got the linear trend line in there. This is actually an Excel spreadsheet. I took his data and made an Excel spreadsheet out of it. And so that is what linear regression kind of looks like. It gives you the most accurate, least error-prone path for that line. Excel will also give you the formula for that line. And we'll talk a whole lot about the formula for the line here in a bit, but just look at that and see that we have a formula for that line. And I said it's not always a good interpreter or predictor. Here's another example of data. Here, you know, that's a parabolic, nonlinear, it's nonlinear, and so a linear regression is probably not appropriate. However, and this Anscombe guy, he had very high attention to detail. He plotted those points in such a fashion that the formula came out the same as the other plot. And he didn't stop there. Here's one where we have a very nearly straight line to begin with, and it only has one outlier. And you can decide whether or not that outlier needs to be in there or not, but it has exactly the same formula as the other two. And one final example, and this is why it's called Anscombe's quartet. He's got 4 examples. We have a very nearly vertical stack of plot points with one outlier again. And as different as that is, as all the others, it has exactly the same formula again. So this is part of what data analysts and data scientists do. They decide, okay, how are we going to plot the data? We're going to work with the type of stuff that's in the upper left-hand corner mostly. and not get into the other things. And that would be a good subject for another meeting. Any questions here so far? All righty, we'll continue.
So far, so good.
All righty, thanks, Mike. So here, and this is an actual Excel chart that I made. I plotted just 5 points on there. And what a lot of people like to do is they like to quite literally connect the dots so that they can tell, they can see trends more often. And let's pretend that these were sample sizes for how much data we used on a hard disk. And between 3 and 4 here, somebody did a DBCC shrink DB, for example, to reduce the size of an MDF file. If you consider all 5 of those points, that's what I'm calling a multi-point sample. If you look at the start and the end points and you only consider those, that's what I call a 2-point sample. Now, the 2-point sample is kind of cool. If you draw a line between those 2 points, you end up with Excel giving you a line that looks like this in this particular case. And just to point out, we'll talk more about what this formula means, but the R squared there is what's known as Pearson's correlation coefficient. Yeah, correlation coefficient. And it's a 1 here. A 1 indicates that every point is on the line. And by definition, when you have 2 points, the line has to contain both of those points, or the line isn't representative of the 2 points. So the closer to the line that they are, the higher that coefficient will be. And if they're all spot on the line, it'll always be a 1. So the 2-point samples will always have an R squared of 1. And we'll talk more about R squared later on. I just drew up the line for the multi-point sample. It's this green dashed line. And of course, it has its own line formula that considers all of 5 points. And I know 5 points is kind of small, but I just wanted to keep it realistic for now. We'll do, a couple thousand points here before the end, but just wanted you to see that it draws this line so that all of these points are as close as possible to the line. And they call that minimizing the error. And that's pretty much what linear regression does. Which line minimizes the error for all the points to give us the best possible trend. All righty, any questions there so far? And Mike, I'll tell you what, if you can just tell me if there is one if you want.
Yeah, I'll pipe in.
Okay. Alrighty, so I keep talking about these formulas. And the reason why I keep talking about formulas is because SQL sucks at charting. And it can't read charts or do any of that. It can only do math formulas and things like that. And so if we have data stored in the database, we can calculate these formulas and we can make some predictions without having to go anywhere near a chart or Excel for that matter. For example, again, these 5 plot points might be this space used, and this black line I just put up here, this black horizontal line, might be the limit. And what's the limit? The limit is the physical size of the hard disk. So a couple of things that we might want to know is, when are we going to run out of disk space? In other words, when will our disk use amount reach that limit? Well, there's 2 places where we can figure that out. The first place is on our 2-point sample. So we would reach this at just a little after, say, month 7. And our other sample would be just a little bit after month 8. There's another thing that we can do, and this is what, and I'll show you a larger example, but what you might want to say is, okay, we want to make it to the end of the year or to some date. And we have this growth rate. How much hard disk space do we need to add right now to try to make it to the end of the year? So we can actually figure that out again without having to go to a chart. We can figure out what that point is at that point in time, in this case, a 9, and we can figure out the multi-point sample as well. And if you add 10% to that for kind of a buffer, you'll be in pretty good shape. So you can predict out, say, a year, so that you're not in a dead panic when I tell people, if your net ops team is telling you when you're 1% free, you are in deep kimchi, because it can get it can go from 1% free to pretty close to 0% free very, very quickly if you're not careful. All right, so the formula for a line. All vertical straight lines have one formula, and all non-vertical straight lines have a different formula, but it's all the same formula for all the different lines. And in linear algebra, and you've probably had this drilled into your head, and I'm going to give you nightmares from high school algebra, y equals mx plus b. In statistics, they decided to mess with us, and they say, okay, it's y equals b sub 0 plus b sub 1 x, and it's the same. It's just they decided that, okay, this is theirs, and they wanted to create different symbols, and there's actually a good reason for the different symbology, and they changed the order on it. So here's the key for both of these. Y is what's known as the dependent variable, and that represents the vertical axis, and that's in both formulas. And the reason why they call it a dependent variable is because if you make changes to any of the other constants or variables, Y has to change. Okay, X is an independent variable, and this is typically the horizontal axis, and it can be, for this storage, it would be dates. For something like how many cones you're going to sell, for temperature, it might be the temperature of the air. So we got the value of X here, and up in linear algebra, we can see X there, and it's also called X in statistics. That much stayed the same. And then we end up with B or B sub 0. I think that formula stinks, so I refer to it as BO, but that's just for fun. B is up here in linear algebra. It's standalone, and it's called B sub 0 in statistics. It's the same thing. This represents the y-intercept, and we'll see what the y-intercept is here pretty soon. And then we have M. M is the slope of the line. And up here in linear algebra, you can see y equals mx. And when we say mx, that's m times x plus b. Or you can see it here as B1 in statistics. Any questions on this so far? Anybody having high school nightmares? Okay.
Yes.
Yes, you're having high school nightmares?
Correct. And here I thought it was long enough that I'd forgotten about.
So why do we want to do this in SQL? And the answer is because the data frequently lives in a relational database, and we don't always have other software available. And for something like disk space usage, we don't want to actually go and use other software. We just want SQL Server to, on a nightly basis, go take a sample and let us know, and maybe email us something in a morning report. If other software is available, like Power BI or other things like that, very much like we saw in the crosstabs lesson that I gave, sometimes you can do things in SQL Server that will blow the doors off of other methods for performance, and then you can have these other tools actually do the formatting for you. So it's a form of keeping the data layer separate from the presentation layer. And in this case, we're going to do a little bit of both. And that's the the purpose of this presentation. We're going to provide an introduction to what linear regression is. We actually did that just now. We're going to show you the two different methods and the related formulas. We're going to learn the formulas for those and learn the simple code methods. It's actually very, very simple. It will look horrible until you realize, oh my God, SQL was built for this. And then we're going to learn how to manipulate those formulas a little bit to determine things like the predictions that I was talking about, like, hey, what date are we going to run out of room? Or if we go out to this date, how much room do we have to have? And like I said, we're going to do it all in T-SQL. So, calculating 2-point linear regression. Again, we have our 5 points here, and we have our starting point at x equals 1, y equals 2, and we have our ending point at x equals 5, y equals about 6.5. And for a 2-point regression, we have to draw our line through those 2 points. And Excel comes up and says, yep, this is what the formula for that line is. So we have to write some code that will give us these numbers. All righty, in case you forgot, slope is the rise over the run. And according to Excel, for this particular set of data, we need to come up with a slope of 1.125. So from the height of our first point up to our second point, we have a rise of 4.5, 1, 2, 3, 4.5. And same thing with run, 1, 2, 3, 4. And we can actually start to apply some points for, or some labels to our points. We can say, hey, our first point, we're going to call the x value x1 and the y value y1. And for our second point, x2 and y2. And then we can say, all right, what's the formula for rise? And the answer is y2 minus y1. And what is our formula for run? And the answer is x2 minus x1. Really, really easy stuff. And so we can put that up here in our formula, and then we can start to do stuff. If we look, we see that our first point is at x equals 1, y equals 2, and our second point is at x equals 5, y equals 6.5, and we can just plug those into that formula. And, you know, of course, SQL Server is going to be very good at doing that. If we simplify that, that comes out to 4.5 divided by 4, and those with Granny's 4-function calculator can figure that out. It comes out to 1.125. Any questions here? All righty, let's continue on. Now, one of the things that we have to do is we have to search for B, which is the y-intercept. And there's a reason for that. And why did this happen? There we go. Hang on a minute. Get the smoothness back. So the original formula is y equals mx plus b. In order to get b all by itself, we have to subtract mx from both sides, which we've done in red here. And then if we look at the right-hand side, mx minus mx cancels out. And so we are left with y minus mx equals b. If we flip that around, we end up with b equals y minus mx. That's the formula for calculating the y-intercept. And if we look over here at the same chart that we've been looking at, first of all, what is the y-intercept? And the answer is it's where that line crosses the y-axis. Another way of thinking about it is if the value of x is 0, that's the value, that y value is what the y-intercept will be. That's the figure of b. And that's also why in the other formula they call it b sub 0. It's b when x is equal to 0. All right, so Excel is telling us B has a value for this line of 0.875. And we already know what the slope is because we calculated that before. So if we take the numbers here for our first point and we plug them into this formula, y is equal to 2, the slope is equal to 1.125, x is equal to 1. We do the simple multiplication there and we end up with that. And if we simplify that, we come up with 0.875. Now, the really cool part is this is a straight line, and every point on that line is at the same slope as every other point in the line. And so that means that B should be the same no matter where we're at on this line. And so we can take the data from the second point and we can plug that into the formula where y is equal to 6.5. Again, the slope is equal to 1.125, and the x value for that point is 5. And if we do the multiplication, we end up with 6.5 minus 5.625. And if we do that simple bit of math, that also comes out to 0.875. So again, just to reiterate, the formula for B is y minus mx. And I know right now you're going, why in the hell do I need to know what B is? Trust me, we're going to get there. Any questions?
So far, so good.
Alrighty, thanks, Mike. So here's the code for solving M and B. Now, in the upper right-hand corner, you just saw demo come in. Anytime you see demo there, I'm going to give you a demo. Or if it's code, it means I may have already given you a demo and we're just going to cover some more code. And the other thing is, when you get the zip file, the name of the file for the code being displayed is up there as well. So we need to go and look at script 300. You might ask what happened to script 100 and 200. And that would be a good ask. And that's the wrong one. Let's try this again. Actually, hang on just a minute. Big time cockpit error tonight. It's not working. Here we go. All right, so what I want to show you is if you open the zip file, and I have the files already separated out, we have all these files, and if you flip on the name to get them to sort in reverse numerical order, and you select them all, why is this not working? There we go. If you select them all and say open, they will open up in SSMS with the lowest number furthest to the left. It just makes life real handy. And I'm going to put these two first ones up a little higher. Script 100, and you can go back and read this, and all these scripts are fully documented, but what this is going to do is it's going to create a database called Linear Regression _ JBM. I'm not trying to be a pompous ass here. What I'm assuming is that you're not going to have very many databases that have a suffix of _JBM. And so there's a pretty good chance that I'm not going to actually drop a valid user database for you. So if we run this, we can also see that it has created a couple of other things here. We'll get to those other things a little bit later on, but it created the database for us. And then we also want to create some data. We have 3 tables. We have a small test table with 5 rows, a disk used table with 98 rows, and then a slightly larger table with, this is our multi-disk used example with a little over 2,500 rows. And I've tested this method on a 100 million row table, and it's fast. It is really fast, especially if you have the right index on it, and you know, for the table scan. All right, so we were going to talk about script 300, and what I'm going to do is run script 300. And what you can see here is we have x1 and y1, x2 and y2. Those are the values of our 2 points. And then m and our b values calculated according to the points that we have. And let's go just take a look at that over here. It's a little easier to see here, I think. If you notice, I'm converting x and y to float. And we'll talk more about why I do that in a little bit, but we're reading that from the small table. And this first part is getting our first coordinate. This gets our second coordinate. And so we're necessarily hitting the table twice here. And then we simply display those two sets of coordinates. And we're going to calculate the slope. The slope is equal to the rise over the run, y2 minus y1, etc. And if you look, we're doing that down here. We have y2 minus y1. Of course, we have our table aliases here. We have y2 minus y1 divided by x2 minus x1. But we also have this null if. If x2 minus x1 is equal to 0, that means that you have a perfectly vertical line and you can't calculate the slope. And so we're going to change that to a null to say, hey, if it comes back as a null, we have a vertical line. Our y-intercept, not so hard. I'm doing both examples here. For the first one, I'm doing the first point of y1 minus the slope times x1. And I do that in both cases, except where did my mouse go? We have y2 minus the product of slope times x2. Any questions on these so far?
I have one.
Okay.
We did the math for the slope in the cross supply to dry it out, right?
Yes.
Thank you.
Yes, exactly. What drying it out means is the front enders have a good term that, and having been a front ender more than 20 years ago, the term dry means don't repeat yourself. And we didn't actually repeat ourselves here very much, but it is going to come up where the formulas get a little bit more complicated, and we're going to use the same values like the sum of x, for example. We are going to end up using those more than once, and so we're going to dry those out. So, good question. All righty, so what we ended up with when we ran the code, again, we were looking for the 2-point sample, and this was the formula that Excel came up with for this line. And we came up with our x1 and x2 just to show that x1 and x2 were at 1 and 2, and this second point was at 5 and 6.5. And if we look, it calculated the slope correctly, and didn't matter which point we used, it calculated the y-intercept, or the value of b, correctly. And you start to see we've got y equals mx plus b down here. And again, Pearson correlation coefficient is 1 because by definition, in order for this line to exist, all the points, which are 2, have to live on the line. Alrighty, multi-point regressions. Again, this is what Excel returns for the line. Your colors will vary. I tried to make it a lot different. And we notice the Pearson's correlation coefficient has changed here a little bit. It's no longer a 1. It'll get closer to 1 when the points are closer to the line. And again, if all the points are on the line, their correlation coefficient will be 1. Turns out that none of the points are on the line this time, but 0.75 is very, very high. If you go and read up about Pearson's correlation coefficient, it doesn't start to get bad until you get down to something less than 0.5, I think, if I recall correctly. And they just mean, you know, how good a representation is our trend line. So, and I've got the links here. In the following formulas, this lowercase I, which looks like a lowercase j backwards, it means for every row. Here's the formula for M. And this kind of stuff used to drive me nuts. And then I figured out how to actually do it. And here's the formula for B. Alrighty, looks pretty complicated, but it turns out that SQL Server is beautiful for these formulas. If you look here, I've got these X and Y values. Those are the only things that we know. We have to calculate everything else. And if we take a quick little look, if we look at these funny looking back E's, that is the Greek letter of sigma, and it stands for sum in mathematics, as in S-U-M, not S-O-M-E. So this is saying, hey, take the sum of X for every value of I. And I is, think of it as the row number. And so it's going to take a sum of this X column, and you can see I've got 1, 2, 3, 4, 5 are the values. And if you add those up, that's 15. So that's the sum of X. And we're going to give that formula the label sum X. And then we do the same thing with E to the Y, or the sum of Y. We're going to do exactly the same thing, and the value is 21.5. We also have E times, the sum of E times Y. I'm sorry, the sum of X times Y. I need a drink, I think. So we have the sum of X times Y. This means that we have a pre-calculation that we need to do. If we look at the value of XY here, it's an 8, where that comes from. And this looks kind of obvious, but I have to state it out loud so that people actually understand that we've got two calculations going on here. 2 times 4 is 8. On the next line down, 3 times 5 is 15. And so this column XY can get pretty big pretty quick. And then we start working with things like the sum of X squared. And it's exactly what you might think it is. If we look at this value 9 here, and we go over and we look at the value of X, if we take the square of X, 3 times 3, it's 9. Then on the next line, 4 times 4 is 16. On the next line, 5 times 5 is 25, etc. There's also a shorter formula. Instead of this monstrosity for B, this guy gave a pretty good demonstration. He did the math up here to shorten this formula a little bit. It's remember the formula Y minus MX? It turns out to be in that form. So for B, we can calculate it by taking the sum of Y minus M times the sum of X and divide that by N, which is nothing more than the count of the number of rows in our sample. Alrighty, and then there's R. And that's the biggest formula yet. And again, we have one extra column, derived column, that we're going to need. In the previous formulas, we didn't have a need for Y squared, but we do here. We are going to need a Y squared value here. And this looks all very complicated. And that Y squared value can get very large, and these numbers can get very large. And that, ladies and gentlemen, is the reason why we use float. If you look at most calculators are accurate to 13 digits on the screen, and behind the scenes, they are accurate to 15 digits. Float is 15 digits. It doesn't matter where the decimal point is, it's 15 digits. Now, people say, well, float's not accurate. That's not correct. It's in base 10, it's not precise for base 10. And the reason why is the float in SQL Server is based on binary math, not decimal math. And I would hate to look at it as binary math, but it's quite accurate for decimal math. And there's a whole bunch of things that are very accurate in decimal math. And if you convert them, ignoring those last two digits, it works just as good as a 4-function calculator. And of course, R squared is going to be R times R. We're not going to do this formula twice. We're just going to get a value of that to dry it out, as was previously said, and we're going to do it. So the slope, ready for this? And what I'm doing is greasing you up here to try to make you realize this is not arduous, and you can do a bunch of things as a data analyst. You understand these formulas. You just need to understand how to apply them to SQL Server. If we look at that, that formula has three different things in it: some basic math, some sums, and a count. If we look at the y-intercept formula, guess what that contains? Some basic math, some sums, and a count. And if we look at Pearson's correlation coefficient, oh my God, that monster. It contains basic math, sums, and a count. Guess what SQL Server is really good at? Basic math, sums, and counts. Okay, so let's see how we can do this in SQL Server. Dun, dun, dun. And of course, we have a demo, and we're going to go look at script 310. So we got script 310 here, and we're going to run through all this, but let me just run it for you. And you can see we came up with some values, just so that you don't think I'm pulling any sleight of hand. Look and see that M is at 0.9, B is at 1.6, and R2 is at 0.75. And we've got the other stuff written down. And we have N of 5. We have 5 data points. All right, so let's start working through these formulas. Again, we convert X and Y to float, and we're pulling from the small table, the 5-point small table. If we look here, this is where the workhorse is. Okay, we are doing an extreme dry out. We are calculating N, the sum of X, the sum of Y, the sum of XY, which is the sum of X times Y, sum of X squared. How hard is it? X times X. We don't even have to use power here. And the sum of Y squared, which is Y times Y. Super easy to do, and it has dried everything out for our formulas, mostly obviously naming, and again, drying out the formulas that are coming up. We are getting ready to calculate the sum. We want to return the sum, and it says here, this not the sum, the slope. It says here, the slope is equal to CA dot M. What is CA? It's down here in this cross apply. Okay, I use CA as an abbreviation for, or an alias for cross apply. And if we bring up our formula for slope, we can see in the SQL code, we have N times the sum of XY. N times the sum of XY. This is not hard, folks. We subtract sum of X times the sum of Y. Not hard, folks. Easy interpretation. N times the sum of X squared. Not hard. And then this is a little bit, you have to keep your mouth just right. People mispronounce this, the sum of X squared. It's actually the sum of X quantity squared, meaning that you have to take the sum of X and then square that instead of squaring each individual value of X. So we have sum of X times sum of X here. Not real hard. Up next, B. This is really hard, right? Sum of Y minus the slope times the sum of x, slope times the sum of x, divided by n. Not real hard. And we have the monster coming up, r. And I'm not going to walk you through all of these. What I do want you to see is, and you could individually walk through all these. It's not a problem. It's the same method. But we have this square root. It's not hard in SQL, folks. We got SQRT, and Bob's our uncle. We also did a null if around that square root to say if it has a value of 0, then it's a flat line. And so we convert that to a null, and then in the outside formula of that, we turn that null into a 1 because everything has to be on that same line if it's a perfectly horizontal line. Any questions on this so far? And while you're thinking about that, I want to point out that we do the conversion up here at the top, and then we do the drying out, and then we do the formulas at the bottom. And that's the same pattern that you want to follow no matter what else you do. No, I'm sorry. R squared is just cross supply of R times the cross supply of R. That's it. Does that all match Excel? And so we had this in Excel, and we had this returned as the formula for MB and R. And we had returned this. We had 5 points, and it showed N as 5 points. The 0.9 is equal to 0.9. The 1.6 is equal to the 1.6. And R squared is equal to 0.75. So our code is working just exactly the same way that Excel calculates it. Whether or not Excel is calculating it correctly is sometimes questioned, but most people agree that, yeah, that's the proper way to do linear regression. And I'm sorry, any questions so far?
I'm just glad you make your, I was going to say, I'm just glad you make your code and your slides available later.
Yeah, I hear you.
This is heavy.
All right, so disk growth analysis. And this is similar to, asset growth, profit analysis, number of ice cream cones sold by temperature of day. It's all the same kind of idea. They all make use of linear growth. And this is an actual bit of data from one of my hard disks. If you look down here, this kind of squirrely looking red line. By the way, did this suddenly take on a very heavy yellow tint, or is it still white to you guys?
That's white.
Okay, because I have it set up so that the night light comes on so I can actually get to sleep at night because it knocks out all the blue. So it's looking pretty yellow to me right now. So this red line here is space being used over time. And you can see where, I did some index rebuilds to recover some disk space. And so that left me with flat for a while. And I did another one up here, left me with flat for a while. But basically, that's the growth that I'm experiencing on this particular hard disk. And this is the old disk size, this black line here. And right where that line crosses is when I'm going to run out of room. And so we actually looked at this at that point where the line is, and that was on the last day of 2023. And we looked at that and we said, we need to add some disk space. And this is at 4.1 terabytes for this disk. So just to get us out of the woods for the holidays, we said, can you give us another half terabyte? So they took us up to 4.6 terabytes, and you'll see that in a minute. If you look at the chart, you can kind of eyeball that it would have run out of disk space on 414 or 415 rather, just a little after 414. And they said, yeah, we'll give you your disk space when we do the next Windows update. So at the end of the month, they gave us some extra disk space. And we looked at that and we said, oh, that didn't take us out very far. That only takes us out to about August 15th. And if we look way up here in the upper right-hand corner, that would be the size that we need to make it to the end of the year. And so we need to calculate what that size would be. And let's go to script 320 now and have a look at that. And you can see we got basically two parts. We have the part above that calculates the M and the B and the R squared. And then we have the part below that applies it. And we'll get to that, but let me run it here and you can see we actually get some outputs here. And you can see we get some dates here. Oh my God. We got dates in a chart in Excel. We'll show you how we do that as well. So here's what we got for the M and the B and the R squared coefficient. And if you look, this is actually a perfect match. We've got the float takes it out a whole bunch of different decimal places. And if we look at the last three decimal places here, it's 137. So the 7 rounds up to make that 14 over here in the Excel output. Then we run into a problem. It's different, but it's the same. And I'll explain what I mean by that here in a minute. I just want you to see and note that it's different, and we'll find out the reason why it's different here in a minute. But R2, yeah, it's also spot on. The 45916, the 6 would cause the 1 to round up to a 2, and that's not enough to cause a roundup for the 9. So, you know, it's left at 459 out here. So it's all the same. And our plot points were plotted out in the second part of the code, which could have been included in the first CT, but I wanted to keep them separate just so that you understood what was going on. And it actually calculated an accurate date of 4/15, 8/15, and the size for the end of the year at 5.181 terabytes, unless I do something. You know, I got to do something. So that's that. And let's go see how it works. Okay. Once again, here we have code and it has the file name. We're not going to do the demo. We already did the demo. We're just going to talk about the code. So the only thing that changed between this code and the 5-point code was, number one, we had to change the column names. And number two, we had to change the table name that we were getting our original data from. That kind of sucks because that means that you can't put this into a function, and you would have to put it into a stored procedure. You would have to use dynamic SQL. And that's not so bad, but I wish Microsoft would say, you know what, metadata needs to be able to be variable, and that would be really nice. The only other thing that changed was this into. We wanted to save our disk results here so that we could save the M, the B, and the R squared. Everything else is exactly the same as our 5-point example. All righty. Any questions here so far? All righty. So we solved a couple of dates, and the dates are on the x-axis. And, you know, we said, hey, how are we going to do this? So we have our original formula, and we are going to subtract b from both sides, first of all. and the b minus b cancels out. And so we end up with y minus b equals mx. And to further isolate and get just the x out on the right-hand side, we have to divide both sides by m, and the m divided by m cancels out, and our final formula is y minus b divided by m equals x. And we can flip that around just to make it look more like what we're looking for. What we're solving for is x. It's on the left-hand side, and that will be equal to the value of y minus b divided by m. Okay, this is all high school math. Everybody makes a big deal out of linear regression. It's no big deal. All right, so we want to solve for the outage dates that we were seeing before. We had two different outage dates. And if we go over here and we look at, I'm sorry. We don't have to go over to script 320, we're still there. Remember this output? And we had this as the linear formula output. At the bottom of script 320, we started to have this data. Now, the sizes that we're getting ready to declare become limiting values of y. In other words, hey, what's our old disk size and what's our new disk size? Those are values of y that we have to run into our two lines so that we can come up with a date when we are going to run out of disk space. And that date is going to be one of the dates that we want to calculate is the end of year date, and that will also become a known x. So this is really hard, right? We'll declare the old size in megabytes as float, and I happen to know that it was actually that number, that exact number of bytes. This is 4,095 megabytes or 4.1 terabytes. And the new size is 4.6 terabytes. And the end of date that we were working with was not exactly the end of the year, thanks to weekends. And then we wanted to predict the out of space dates. Okay, so the out of space date for the old size is real easy. We take our old size and we're going to use that as a limit for y in that y minus b divided by m formula. And that's what this line represents, is the y minus b divided by m formula. And then we convert it to date time. Now, this is the beginning of the magic here, folks. Date time, you can do direct date math with date time. And you can convert what's known as a date serial number to date time, or a date time to date serial numbers. And it turns out that float perfectly holds it all. It's wonderful, and I'll demonstrate that here in a minute. You cannot do a direct conversion from float to date. It'll say, I'm sorry, Dave, you can't do that. Date time is really, really smart. They were really incredibly smart when they created the functionality for date time. And I'm so, pardon my French, pissed at Microsoft for not allowing that kind of intelligence to be built into date and date time. It's a good thing I don't live closer to Redmond. That's all I can say. Also, we can do the same thing for our new size. We have our new size. We want to know when the lines are going to cross, which indicates the date that we're going to run out of room for the new size. Again, we have our new size as this y in the y minus b divided by m formula. And we convert that answer to a date time and then convert that to a date, and that will give us the actual dates. And we'll talk, like I said, more about date time here in just a minute. And then we have our end of year size. Well, we have our end of year date, and it turns out we're just going to use the normal formula of y equals mx plus b. We know what m is, we know what b is, and we just told it what x is. It's going to calculate y and say, yeah, here's how much space you actually need to make it to the end of the year. And again, we have to convert that date to float to get it to work as X. All right, and again, we're selecting from the table that contains this M, B, and R squared data. We didn't use R squared, but it's very high. It's 0.95, so we're doing pretty good here. So very, very easy. Again, Y minus B divided by M, and that allows us to calculate the dates. The date times have to be handled using float to do the calculations, and then very easily we can convert them back to dates and times. Alrighty, date serial numbers. Holy shades of Y2K. This goes back, way back to the first time that I ever saw Excel. And yeah, that was so long ago when God said, "Let there be light," I threw the switch. Remember this discrepancy where we had the 351 versus the 360, and I said that's explainable. The reason, the date serial number for SQL Server has a different start date than the Excel date serial number. That base date is sometimes called the epoch date. It's the date where the underlying date serial number is equal to 0. The really bad part is Excel also thinks that 1900 was a leap year. The rules for leap years, you know, everybody knows the rule, hey, evenly divisible by 4, it's a leap year. No, it's not. If it's also divisible by 100, in order for it to be a leap year, it also has to be divisible by 400. And apparently the rocket scientists at Microsoft didn't know that when they made Excel. So let's go take a look at script 330. And what I'm going to do is, let me zoom in on this just a little bit more. So we have 1900-0101, we have 1900-0229, and we have 1900 1st March. And we're going to do a try convert on all of those to date time. And when we run this, you can see it didn't pass on the 29th of February, because the 29th of February should not actually exist. It converted the other two just fine. If we try to convert these to float, obviously it's not going to do anything for this 229, but I left it in there anyways. So we're doing the exact same formula that we did above to convert to actual date times, and then we're converting those date times to float to see what the date serial numbers are. And we can see the 1st of January 1900 is day number 0, and the 1st of March, which is 59 days later, is a 59. A date serial number represents the number of days since the 1st of January 1900, both forwards and backwards. There's negative numbers prior to that. Okay, and the other thing I wanted to show you here was if we go to Excel, and actually I already have it here, we have 1900-0101, and I'll zoom in. And that came out as an actual date. I'm just going to get rid of these. These all came out as actual dates. Excel didn't bark at these. It took this as a date. And so if we say, let's copy these dates over to here. And what we're going to do is we're just going to simply convert these to the general format, which is numeric. You could convert it to numeric if you wanted to as well. And you can see it says the date serial number for the 1st of January is 1. And it validates that this is actually a date, and it's saying, yeah, that's got a date of 60. And the 1st of January or 1st of March is actually date 61. So between the error that they built into Excel, and people say, well, Excel was there first. Yeah, but Excel was the first to be wrong as well. With the 2 days, you can be pretty screwed if you try to convert data or copy data from, let me rephrase that. It's not all data. If you copy the y-intercept to Excel, you could be in trouble. You can do all sorts of calculations you want, but if you try to copy the y-intercept that you calculate in an SQL server over to Excel, you could be in trouble. So don't do that. Keep it all in Excel or keep it in SQL server. All right, what's next? Multi-line analysis. And Mike just asked the question. Any questions yet, or people's brains started to ooze so far?
Actually, let me check. Nope. I think we're getting oozy, but we're good.
Okay. All righty. So here's the code for multi-analysis. And again, we have another demo. And let's go over here to script 340. Dun, dun, dun. And I'm just going to run this. And you can see we have 2 outputs. And we'll explain what these outputs are and what the sections of code are. There are 2 sections of code. So first of all, this is very, very similar to, remember I said all these linear regressions have 3 sections, and for the most part, they're the same until we get to multi-line analysis. And then there's a tiny little difference. The difference is we needed something to group by. We wanted the system name and the drive letter. And then everything else is pretty much the same. We just needed to make sure our column names were correct. I added disk size just so that we could plot against it. And it's a different table. And I also said, hey, I want you to start your analysis on the 25th of September instead of doing it all. But basically, this is the same as the little 5-point analysis. It's just we have a couple of extra columns that we added. The same holds true here. Same as the 5-point analysis, except we need to have columns to group by for our system name and our drive. And this disk size just comes along for the ride. Other than that, it's identical to the little 5-point example that we have. And the group by is extra here as well. And then this is pretty much the same, except for the exact same things that we just said are different. We include our system name and our drive name for reporting purposes. We have our disk size in megabytes. We're inserting this into a different table here. And this is the result that we get from this. We're doing our grouping by the system name and the drive. And I'll show you the raw data here in just a minute. But then we have, you know, the big 4. We have N, which is count, M, which is the slope, B, which is the y-intercept, and R2, which is the Pearson correlation coefficient. I do want to point out here on line 4, we have a negative slope, and we'll explain that in just a minute. And the disk size here is there for calculation purposes. And you can see that was all of that down to here. What I wanted to show you, this gave us our output. What I wanted to show you just real quick was what the data looked like. And that was actually over here on script 200. This data is this big data. It's got all this data, and it's as a CSV. Let me get up to the top of that. So nothing special about the table. It's just got sizes there. And you can see we have the status date, the system name, the drive letter, and then the size of the disk, 3 megabytes, and this was actually calculated before I put it into this. And I also want to show you how we get this here in a minute, but there's 2,500 rows in this, 2,520 to be specific. So this first part only calculated the big 4, and that little bit extra came along for the ride as a max. And then we have this second part. Again, this could be the CTEs could be combined if you wanted to, and you've already seen this run. So the what I did was I declared this end of year date, and I also put in a purchase buffer of 10%. Now I didn't actually use the purchase buffer here because I didn't want to cover too many things at one time, but I put this here, the purchase buffer here, to remind you, you could add that into the size and do the calculations. But the max size for the out of year date, it's another y minus b divided by m type thing. We've got the known disk size that we want in there, and it just works. And the same thing with the end of year size. We have an end of year date, and that's just using the regular y equals mx plus b formula. And then here comes the artificial intelligence. Dun, dun, dun. Yeah, it's not artificial intelligence. It's just good code. This is what they call machine learning. And it's all based on all the linear regressions that we have. And we're saying, hey, under these conditions, we'll be out of disk space before the end of the year. Or if we're under these conditions, it's okay. We don't actually see any growth on this disk. For that K drive where we had the slope, the negative slope, yeah, that's going to need some special looking at to make sure that we're going to be okay. And otherwise, it's okay. It's growing, but it's okay. We're not going to be out of space before the end of the year. And what that gives us is this. It gives us our grouping. It gives us our original data that we had calculated in the table. And it gives us our little extra here for plotting points if we want to. But then it gives us our out dates. It's saying, hey, our C drive, yeah, we're not going to run out of room on that until 2032. It's okay. It's growing. Here, yeah, we're going to run out in 2025, shortly after the first of the year. But right now, it's okay, and it's growing. The K, it was supposed to run out of room according to what we did because we have a negative slope back in 1971. So we need to go and look at that. What had happened was the K drive is a working drive for DBAs where we work. And when we took some samples, we had some big stuff in it, and we got rid of the big stuff over time. And so it had a negative growth rate. We also have the end of year size. Here are the sizes that it's going to be for the end of the year. So if it says okay, we don't have a problem. But if it says out before the end of the year, we've already calculated how much disk space we need to be there, so it doesn't run out before the end of the year. And of course, we have the condition of our disk laid out in English terms, which people call machine language and AI and a bunch of other stuff. All right, so I want to give you some links for drive size code. I'm glad Ed showed up tonight. Ed actually has an article out on SQL Server Central, and he does a deep dive on a whole bunch bunch of stuff. It doesn't have any mount points, and the example I'm getting ready to show you doesn't have any mount points either. It only shows you drive letters. But there's some excellent discussions that follow in that article. A guy by the name of, I think his last name is Whittle, Perry Whittle, talks about what you can use to do the mount points. And if you do a general search, there's a whole bunch of different things. Or don't tell anyone, you can do it my way. We're going to go look at script 100 for the record disk status stored procedure. And we're going to look at script 400 for some command line usage, WMIC commands to interrogate the disk with. And you can either use PowerShell, or the shush part is, I don't bother PowerShell. I call it through XP Command Shell. I actually met Ed Wagner because he came to see my my presentation way back in 2013 on how to use XP Command Shell safely, because he loves XP Command Shell too. All right, so back here in script 100, I said we wanted to go and see record disk status. Come on. Well, that didn't work. And this is a stored procedure. Now, this is a simplified version of the stored procedure that I use at work. It requires XP Command Shell, a function called the limited split 8K. If you have SQL Server 2022 or above, then you can use the improved version of their split string, or string split. But it does need the ordinal. And here's the magic. It's just a call to XP Command Shell, and it gives a list of the different things that we want it to show. We can see it run right here on this machine, which has a lot fewer drives. But we can see my C drive, my D drive, and my E drive. And notice I didn't add node here. Node is not something that you can add here. When you add the format CSV, that's what adds the node. And if we go over here to script 400, we can see more examples of this. Here is the example without the node. This does not return the data as columns. It returns it as full line strings that look like they're in columns. If you convert it to the CSV format by adding the format, the / format CSV, that gets converted. And if you really, really want, just to get you here, if you look at WMIC, if you use WMIC volume instead of logical disk, and you can say get along with the / question mark, it will describe the different columns that you can get. This is kind of like doing a PowerShell thing to tell you what you want to look at. But let's go back over here. And you can see when this runs, XP Command Shell is going to create an output, and I capture that output and stuff it into a temp table, and then we parse that temp table using the limited split 8K. Again, you could use string split in 2022 and above. It won't work for 2019 or below, because we need to know which column we're pulling up, and only the 2022 version will give you the columns. So, but the limited split 8K is built when we build this database. If you look, I don't have it here, but it said, yeah, I'm building the limited split 8K for you. So it's all there. Now let me get back to script 400. And I think we're done there. It was script 100 here. But anyways, this does the splitting and adding it to the columns, and then it does an insert into a table called this status, and it converts the whole number of bytes to megabytes, et cetera, and it calculates the used megabytes for you. And that's it. All righty. So just a quick review. We learned what linear regression is. Some of us probably knew what it was, and at the very least, we gave some people some nightmares from high school algebra. It allows us to predict the future based on history. We learned two different methods. We learned the 2-point method, which skips outliers and flats, and we saw Anscombe's quadrant or quartet, where we saw, hey, you know, you can get similar line values for totally different lines. So you do need to be careful on what you use it on. And we learned the multi-point method, which considers all of the points. We learned the formulas for basic linear regression, and they're ugly formulas. You know, there's sums all over the place, but they all boil down to y equals mx plus b, or y equals b0 plus b1 x for statistics. And then we learned the formulas for slope, y-intercept, and Pearson's correlation coefficient, otherwise known as R squared. We learned the simple code methods for linear regression. We saw that all of the formulas were just basic math sums and counts, and that's really easy to do and really, really fast for SQL Server to do. And you saw how simple the code was. It had three basic sections. The first section converted X and Y to floats. The second section calculated all the sum X, Y, those types of sums. And then the third section just did the formulas based on those. We learned to manipulate the Y equals MX plus B to help forecast some of our linear regression so that we can figure out, okay, our hard disk is going to run out of space on this date. And if we want to make it out to the end of the year, is how much hard disk we need to have. All sorts of good things. You can now let your imagination go wild. And we did it all in T-SQL. And as a sidebar, we also learned that date time is incredible for doing date math. Absolutely incredible. We also learned that about date serial numbers and the fact that Excel uses considers 1900 to be a leap year when in fact it was not, and it also has a different epoch. It uses it actually uses the December 31st of 1899 as the epoch date instead of the 1st of January. And again, the epoch date is when the underlying date serial number is equal to 0. And the date serial numbers represent the number of days since the epoch date. And very powerful stuff that you can do with that. So we saw this, and we actually went through and we found all of these points doing all these different, doing some really simple code. And we talked about all of this and how to calculate these dates and how to extend that date. And then we also talked about, okay, that's for one disk. How do we do that for 13 disks, and we did that. And with that, there's our multi-analysis. And we did some really cool stuff with that. You could actually box that up with a little HTML and have it sent to your desktop every morning. References, just some recommended reading. This is good for the 2-point slope. This is good for the M&B formulas and how they are actually derived if you wanted to do a deeper dive on them. And they have more complex regressions other than just regular linear regression. Some interesting tubes with great explanations. This guy that did the tubes on this page, he explains how linear regression works and why it works. And it's fascinating to watch. They go a little bit slow when they're typing numbers in, but he explains very well the actual function of linear regression on all of these. The problem with his formulas are they require 2 passes on the table, just like the 2-point thing does. Whereas for our multi-point, we did it all in a single pass. And on that subject, there's some references for the multi-pass or the single pass. And this is also the guy that greatly simplified the equation for calculating B. And that's it. Are there any questions while we're here? Now's the time to ask. Mike, did you fall asleep on me?
No, I'm here. No, it's I think everybody gets the end of your presentations and are just like in a daze. So Jeff always does provide the slides and the examples, the code, and I get those posted up. I'll post them in comments in the meetup event for this, so you can look for those if you're. And we can talk about some follow-up if you can't come up with anything to talk about right now. I imagine once people start playing with this, you may have some questions.
Yep.
But in the meantime, if go ahead.
Feel free to ask them, just in case. Just in case.
Good job, buddy.
Yeah, this was excellent.
There's my public email address if you have other questions again. And I'm sorry about the brain meltdown, but it really helped me with, I don't have very many servers, but one of the, like Ed says in his article, one of the most embarrassing things that can possibly happen to a DBA is to run out of disk space.
Yeah, because when you do, it's never a quick fix.
No, in
and
fact,
if you need a quick fix, it's painful because it means, okay, now you got to pick, something's going away, and nobody likes to have their stuff go away.
That's a fact. And sometimes the rollbacks aren't so friendly.
No.
I have seen rollbacks take 10 hours to complete.
I've seen all that.
Yeah. Alrighty. Well, one of the things I want to do before all y'all leave is this. I want to thank you. You folks are making a difference. You might not realize it, but you're coming to training. Free time for anybody in IT is difficult to come by, and you guys just spent, I don't know how much, maybe an hour and a half.
Hour and a half, yeah.
With your free time listening to me. And I just want to say thank you very much for what you do, because you're making a difference out there. And, you know, now you can help maybe teach somebody else. Thank you very much. I appreciate it. That's it for me, Mike. You
All right,
Kill the
I'll go
recording,
stop.
buddy.
I'll stop the recording now.